Hi there, welcome to Bitbee. My name is Tirupati Rao, author of Bitbee. Today we are going to explore about one of the important sorting algorithm, that is merge sort. So we'll go through merge sort algorithm and its visualization with example, implementing the merge sort in Java and Python, and finally we'll explore about the time and space complexity of the merge sort. Let's start with the algorithm and its visualization. The merge sort algorithm also falls under the divide and conquer strategy. In quicksort, we have observed that it follows the same strategy using a pivot element. But here in the merge sort, the difference is there will be no pivot element. Instead, the array will keep getting divided using a mid element or the mid index. Now let's take one input array to visualize the merge sort algorithm. So as a first step of this algorithm, we will keep dividing the input array until we found one element each. So here in the visualization, you can observe that both left and right side the array is keep dividing until it reaches the one element each. After this, we need to repeatedly merge the partitioned arrays to produce a new sorted arrays. That is in reverse. Now we need to merge the divided elements and we need to sort them when we merge. So now let's try to sort the elements in ascending order. So in the first iteration, the 7 and 3 will be compared. So 3 will come first, then 7. So here when I am merging back the sorted arrays, you can observe one thing. To merge back the sorted elements, I am using the same unsorted partitions which we got from the original array. So this process continues. Again, two sorted arrays will be merged into one by comparing the elements from both left and right. And so finally the two big sorted left and right arrays will be merged again. You can see that here in the final stage, the elements from left and right subarrays are compared and they are positioned in a right place in the final sorted array. So overall, the merge sort has two simple steps: divide the array and merge back the subarrays, right? So now let's see what is the pseudocode for this algorithm. So here I have written the pseudocode for the merge sort. It will take the input array, the lowest index and the highest index as parameters. So until low reaches high, that is low less than high, we will keep dividing the array, right? So mid equal to low plus high by 2. This is how we will get the mid. And we recursively call the merge sort for the left and right subarrays to keep dividing until we get one element each. Let's take one more sample input array with different values. So I'm taking one more time the example to visualize the array with indexes. So here from the example, the array low is 0, then high is 4, right? So if we trace this recursive call on these indexes, this is how it is divided. You can see merge sort left and merge sort right. And finally, when they reaches to the single element each, that is 0, 1, 2, 3 and 4. And we need to merge them back using a merge function. So here is the pseudocode for the sample merge function. I have written the steps of this function in detail so that you will understand easily. Now let's try run this function. As a first step of this method, we need to create a empty array in which we will sort and put the elements. And at the beginning of this function, that is in the first call, we will be with the subarrays with the indexes 0 and 1, right? So we'll start comparing the elements from here and we will sort them. So here 50 and 90 are the single elements in each array. So as per these methods, these arrays are not empty. We'll compare the top elements from each array. So here 50 is less than 90, right? We'll add that to the new array first and we'll remove that first item from that original subarray. After that, no elements in the left subarray and there is only one element in the right subarray. We will bring that to the new sorted array. So here the element 90 come to the sorted array and it's already got removed from the right subarray. So now we got the new sorted subarray with 50 and 90 and we have right side subarray with one element that is 10. So the same process continue for these two subarrays, compare and put it in a new sorted array, which you can see here in the visualization. This merge process keep continue until we sort all the elements from all the left and sub right arrays and finally will form a single sorted array. So let's continue the process. So now the entire array got sorted, right? And this is how the merge sort algorithm works. You can take one or two unsorted arrays and you can apply this algorithm on those to sort. So you will understand very well when you dry run it. So now let's dive into the coding of this algorithm. We'll start with Java. We'll first write the merge sort method. So here in the class I'm writing the merge sort method. Here we are passing three parameters: array, low index and the high index or the rightmost index. If the low is less than right, we will divide and find the middle, right? Then we will make recursive calls for the left and right sub arrays, and finally we will merge. For that we will make one more call to the merge function. Coming to the merge function, initially I'm trying to declare two arrays, that is left and right sub arrays. Then I'm copying the elements from the original array to these sub arrays. After that, to compare and merge the unsorted arrays, taking two pointers I and j initializing 0. Once we compare the elements at these indexes, we will sort those elements, then we will increment these counters. If you are observing, after comparison, we are putting the sorted elements in the original array, that is previous subarray. And the final step in this merge function is, after comparing the two subarrays, if any elements were left still in the left or the right subarray, we need to put them in the merged array back, right? That's what we are doing in these two whiles. So that is all about the Java code implementation for the merge sort. Even you can just write a driver function, that is main function, and test it. Now I am also popping out the Python implementation for the merge sort algorithm here. You can go through it if you want. Anyhow, I am providing the GitHub link for the Java and Python implementation in the description. You can save and you can refer it anytime you want. So that is all about the merge sort algorithm and its implementation. Now let's dive into the final topic, that is time and space complexity for the merge sort. So if we observe the pseudocode for the merge sort function, there is a base condition which will stop the recursive calls. Of course, inside we have the two recursive calls for the merge sort. Then there is a one merge function. So here we can take the condition will take constant time, that is 1. Again, calculating the mid from low and high indexes, that is constant time again. We can take it as c1 of n. So for the recursive calls, it will make n by 2 time calls, right? Because we are dividing the array. So let's take it as t of n by 2 for each. Then finally we are merging all the n elements, and let's take the time complexity for that as n. So the overall time complexity t of n is equal to 1 plus c1 of n plus 2 into t of n by 2, right? That's what I have written here. So mathematically, if the n is equal to 1, the time complexity is just 1. If n is greater than 1, the time complexity will be 2 into t of n by 2 plus n, and we're just ignoring the constant time, that is c1 of n here. And now I just want you to remind the master theorem in mathematics. If you are going through that first para, what it is telling, that master theorem is a tool in the analysis of algorithms, particularly for solving recurrence relations that arise in the analysis of divide and conquer algorithms, right? So establishing a relationship with the merge sort, we know that our merge sort also follow the divide and conquer algorithms, right? So now according to this, the time complexity formula is t of n equal to a into t of n by b plus f of n, where a and b are constants, n is the size of the problem, of course t of n is the time complexity of the problem, and f of n is the cost outside the recursive calls. So in our case, this is merge function, right? The outside call. So by comparing this formula to our time complexity, we can form a relation between the variables a, b and f of n, right? So here a is equal to 2, b is equal to 2, and f of n, there are 3 more cases exist. Let's see them. So for the first case, f of n equal to O of n to the power c, right? So here n to the power c is equal to n to the power 1 in our case, right? So c is equal to 1. But here it is mentioned that if you see, c should be less than log b of a, that is c should be less than 1. But in our case, c is equal to 1. So the first case will not fit for our problem. Coming to the second case, f of n equal to theta of n log a base b, right? So if we fill the variables a and b for this case, f of n is equal to O of n to the power log 2 base 2, right? And this will give back as f of n equal to O of n to the power 1, which is holding the case 2, right? So hence now if we are fill up our function t of n, which is equal to O of n to the power log a into log n, right? Which is equal to O of n log n. So next time onwards, whenever we face these divide and conquer algorithms, and if we want to trace that problem, you can blindly say time complexity is n log n, okay? Here n is input size. So now let's try to trace a graph for this. So if we take the input array size n in the y-axis and then time in the x-axis, and here you can see the yellow line on the graph which will gives the n log n time complexity. So the time complexity of n log n, we have seen already this for the quicksort, but the difference between the two sorting algorithms is, in worst case quicksort can go to the n square time complexity, but in case of merge sort, even in worst case it will holds the n log n time complexity. And finally, coming to the space complexity, it will take n extra array size, as this is not sorting inline in the original array, right? We are every time we are taking a new sub arrays when we divide and merge them back, right? So that is all about the Mozart algorithm and its time and space complexity. Please subscribe to the channel if you are not yet subscribed, and we'll see you in the next. Thank you.